Good morning, girls. Hope everyone is safe at home. Welcome to our software engineering revision session. Okay, in the previous class, we revised Unit 2 Part 1 concepts, and now in this session, let's begin with Part 2 concepts. So, in this revision session, that is software design, I want to revise these concepts like overview of the design process, how to characterize the design, cohesion and coupling, layered arrangement of modules, and approaches to software design. Okay, now let us begin with the overview of design process. So once we had completed our requirements analysis and specification, that is we got our SRS document ready. So that is the outcome of the requirement analysis and specification is nothing but SRS document. Okay, once this SRS document, that is software requirement specification document, is ready and accepted by the customer, then we proceed with the next phase or next activity, that's nothing but the design. So during design phase, we transform the SRS document to a form which is easily implementable in some programming language. So that means now the SRS documented is converted into such a format using which we can implement it by using any programming language. So now by applying some set of design activities, our SRS document is converted into the design document. Okay, so once we had ended with the design phase, let us see what would be the outcomes. Okay, so these are the different outcomes of a design phase. Okay, the first one is different modules required. So different modules. Actually, first, what do you mean by a module? A module is nothing but a collection of functions and the data shared by the function of a module. So here a function is nothing but it satisfies the requirement which are specified in the SRS report. Okay, so in order to meet the requirements, generally we need to write the functions in the programming part. Okay, so whatever the functions that we should write, those functions are identified, and the similar functions, that is a set of similar functions, are grouped together to form a module. So that means in a module we will be having a set of functions and the data shared by those functions. Okay, so I will show you the module structure. Okay, so this is how the module appears to us. Okay, so in the module we'll be having some set of functions and the data shared among those set of functions. Okay, next, the control relationships among modules. The control relationship between two modules essentially arises due to function calls across two modules. For example, we are having two modules like module A and module B. So let us consider a function in module A need the services of the function which is present in module B. Then in order to use the services of the functions which are present in module B, obviously this module A has to make a call to module B. So that means there is a relationship, there is a call relationship between these two modules. So that kind of control relationships, that kind of relationship should be identified. Okay, so first we are identifying what are the modules, and then we need to identify what are the control relationship among those modules. And even sometimes a module may be subdivided into two modules. Okay, so in that case a parent and child relationship exists between these three modules. That is, a module A is divided into module B and module C. So now module A is a parent and module B and C are the child. Okay, so now we need to identify this control relationship. That means the module A is controlling module B and module C. Okay, so that is the control relationships among the modules. Next one is interfaces among different modules. The interfaces between two modules identifies the exact data items that are exchanged between two modules when one module invokes a function of other module. So obviously whenever a function in one module is invoking another function in the other module, obviously they share some certain kind of data items. Okay, so in order to share the data we need certain interfaces. So that's the reason why we need to identify the interfaces among the different modules. The next one is data structures of individual modules. So a module is nothing but the collection of functions and data structures, associated data structures. So in the first step we had identified the functions, and then we need to identify what kind of data structures are utilized by these functions. Okay. And finally, for each and every identified module, we need to identify we need to produce the algorithms. That means now whatever the modules or whatever the collection of functions that are there in a module, for each and every module we need to write the algorithms, right? So these are the outcomes of our design phase. Okay, so once the design is completed, we will be provided with a set of modules, the call relationships or control relationships among those modules, and interfaces among different modules, the data structures of individual modules, and finally algorithms required to implement the individual modules. Okay. Next, coming to the classification of design activities. So by applying various design activities, SRS document is converted into design document. Now let us see what are those various design activities. So generally these design activities are classified into two forms. One is preliminary design or high level design, and the second one is detailed design. This preliminary design or high level design, and the other one is detailed design. Now let us start with the high level design, that's nothing but preliminary design. Okay, so during high level design, the problem is decomposed into modules. The control relationship among the modules are identified, and also the interfaces among the various modules are identified. So that means, so we had seen the outcome of design process, right? So whatever the first three outcomes are there, okay, these are the outcomes of the high level design. Okay, and the remaining two are related to the outcomes of the detailed design. Okay, so in the first step, during high level design, what we are doing first, for each and every problem identified, here the problem is nothing but the requirement given by the customer. Okay, so now that problem is decomposed into modules. Okay, why we are decomposing into modules? Why to divide a problem into sub problems? Why? Because it is easier for us to solve a sub problem rather than solving a big problem. Okay, so here we are applying divide and conquer principle. So by applying divide and conquer principle, the major problem is decomposed into sub problems, and now that sub problems we are considering them as a modules. Okay, and later we need to identify the control relationship among those modules, and also interfaces among various modules. Okay, so finally the outcome of this high level design is called the program structure or a software architecture. So whatever the modules we had identified, and whatever the control relationships we had identified among those modules, all these are represented in the form of a diagram, that's nothing but a structure chart. Okay, and that is also that is termed as a program structure or software architecture. Okay, so that means in a program structure or a software architecture, the control relationships among the various modules are represented diagrammatically. Okay, now let us see some of the notations which are used to represent high level design. So already I said you the structure chart is used to represent the to represent this program structure or software architecture. Okay, that is the very basic notation used for representing the software architecture. Okay, so this is the first one. Okay, so several notations, among that first one is usually a tree like diagram called structure chart is used. And another popular design representation technique is UML. UML stands for Unified Modeling Language, where we represent the relationships among the various functions in the form of diagrams, and these diagrams are generally classified into 9 different types, like use case diagrams, class diagrams, sequence diagrams, collaboration diagrams, object diagrams, state chart diagrams, and so on. Okay, so by selecting certain kind of designs, we represent the design modules. Okay, and generally this UML is used when our selected programming language is an object oriented programming language. That means, let us consider you are working with Java. That is, you want to write, you want to go for implementation by using Java programming language. So Java is obviously object-oriented programming language. So in that case, you can go for the design part by using UML diagrams. Okay. So by using the UML diagrams, you can represent various designs in the design phase. And some of the other notations are Jackson diagram or Vernier or diagrams. Okay, generally these are very leastly used. Okay, but the most frequently used design models are structure charts and this UML diagrams itself. Okay. So this is how the structure chart appears. Okay, so here we are having some 5 modules: module 1, module 2, module 3, module 4 and module 5. Okay, so here there is a control relationship. We are also representing the control relationships among various modules. Okay, so here module 1 is controlling module 2, module 3 and module 4, and in the same way the module 4 is controlling module 5. So it's something similar to the parent child relationship. This is the parent and these are the children of M1, and for M4, M5 is the child and M4 is the parent. Okay, so in this manner we can represent the various modules and control relationship among those modules using the structure chart. Now next is detailed design. So what are the leftover outcomes of the design phase? The algorithms and the data structures. Okay, so that is done in the detailed design. That is the second activity of the design phase. So during the detailed design, each module is examined carefully to design its data structures and the algorithms. So that means during detailed design, for each and every module we identify what kind of data structures are required, and we also write the algorithms for each and every module. Okay, and finally this outcome, that is the outcome of this detailed design, is called as module specification document, in short MSpec document. Okay, so the module specification document is nothing but it contains the data structures and algorithms of the identified modules. Next, coming to the classification of design methodologies. So generally the design methodologies are classified into 2 types. First one is a procedural oriented or functional oriented. So whenever your design methodology is a functional oriented one, then we go with the structure charts, and the second one is object oriented. So whenever the design methodology is object oriented, then we go with the UML diagrams. And other than these two design methodologies, the very recently introduced the design methodologies are aspect oriented design methodology and component based design methodology. This component based design methodology is also called as client server design methodology. Okay, now let us see the analysis versus design. Okay, so that is let us try to identify how important the analysis and design are. Okay, an analysis technique helps elaborate the customer requirements through careful thinking, and at the same time consciously avoids many decisions regarding implementation. So that means during analysis part, we clearly mention all the customer requirements, we elaborate the customer requirements, and we doesn't mention any implementation detail. So that is the one of the good property of the SRS report. Okay, so in order to become a SRS document, a good SRS document, it is having one of the property that is nothing but implementation dependent. So we should not implementation independent. We should not discuss any implementation details in the SRS document. But coming to the design model, the design model is obtained from the analysis model through transformations over a series of steps. Decisions regarding implementation are consciously made. So here we are much bothered about the implementation details. Why? Because here we are writing the algorithms, and these algorithms will help us to perform the implementation task easier. Okay, so that means we can, but just by seeing the algorithms, just by understanding the algorithms, we can write the lines of code in the implementation phase. Okay, so that means this design module is concentrating on implementation detail. Okay, whereas analysis, it should not discuss anything about the implementation details. Okay, does a design technique lead to a unique solution? Can you guess what the answer is? Does a design technique lead to a unique solution? That means either using functional oriented approach or object oriented approach, whatever the approach you use, does you come with a unique solution? The answer is no. Why? Because even though we are using the same design methodology, different designers usually arrive at different design solutions. Suppose if I had asked you to solve a problem, suppose if that problem is given to some 10 students, obviously the 10 students will come with different lines of code. Okay, we may not get 10 different types of code, but at least we get at least 2 or 3 different codes, different way of implementation. Okay, so that means we can't expect that all the people or all the students will come with a unique solution. In the same way, whenever we are designing any model, even though different designers are using the same design methodology, they may not come with a unique solution. They will come with a different design solutions. And even the same designer can come up with several alternate designs. So obviously true. We may always, we may not think in a say similar manner. That is, we may not think in a one direction. We may be trying to concentrate on any like any, are there any alternate solutions, like we'll be trying to analyze whether there are any alternate solutions. So at the same time, we may come with some alternate design solutions also. Okay, so that means different designers also will come with different design solutions, and even the same designers may also come with the different alternate design solutions. Okay, so that means now for a simple problem or for a single problem, we got different design solutions. Now, how to tell which among these different design solutions is a good design solution? That is, how to obtain a good design solution from these various alternative solutions. So that is the fundamental question that arises to us, that is how to distinguish between the superior of the two alternate design solutions. So unless we know what a good software design is, we cannot possibly design one. So that means just like properties for a good software document, here also we are having a properties for a design to be a good design. Now let us see what are those properties. Okay, good and bad designs. So there is no unique way to design a system. Even using the same design methodology, different designers can arrive very different design solutions. So we need to distinguish between good and bad designs. So we are having certain characteristics. If at all a design is having these characteristics, then we can say that particular design is a good design when compared to the other design. So what are those characteristics? Means correctness, understandability, efficiency and maintainability. Okay, so coming to the correctness, a good design should correctly implement all the functionalities of the system. So whatever the functions that are represented in the form of requirements in the SRS document, those functions, that is those requirements, should be present in the form of functions in the design, and all the similar functions should be grouped as a module. Next one is understandability. A good design should be easily understandable. If not, it would be difficult to implement and maintain. So in the later sessions, let us see how to get this understandability. Okay, so by having a modularity and layered arrangement among the modules, we can have that understandability nature. Okay, and this plays a major role in order to say that the design is a good design. Why? Because without understanding a design, we can't say whether it is good or bad. Okay, so that is the most important characteristic of any design model. Next one is efficiency. A good design should adequately address resource, time, and cost optimization issues. Okay, and next one is maintainability. A good design should be easy to change. That means whenever the customer comes with a change requirement, then obviously we need to perform changes in the SRS document. Okay, so whenever the SRS document is changed, then obviously we need to perform the changes in the design document. Okay, so that means just like modifiable nature for a good SRS document, here we should have a maintainability nature for a good design document. It should be easily modifiable. Okay, so these are the good characteristics. That is, if at all any design is having these four characteristics, then we can say it as a good design. Okay, so here, as I said, you understandability of a design is a major concern. Okay, so given that we are choosing a design solutions from only correct design solutions, understandability of the design solutions is possibly the most important issue to be considered while judging goodness of the design. Okay, so this that's what the importance of this understandability. Okay, so when we can have understandability of a design, that is what kind of nature among the modules, among the design modules, will make us easily to understand. Okay, so that one, that is that modularity, let us see in the, that is a modular and layered arrangement, let us see in the next revision class. Okay, with this now I end up with this revision session, and let us continue the characteristics which lead to the understandability nature of the design solution. Okay, thank you.